saw people start to do. And this is why I explained to you that for factoring, you want to write on your palm GCF. Because the minute people started this, and then they ended up erasing it, but this is what I saw a couple of students in this class do. The minute they looked at this and the word said to factor, this is what they did. They went just like that. Because somewhere along the way, you think that the only type of factoring is to write two parentheses like this and do something like x plus 2, x minus 3, whatever. That's for second degree trinomials or fourth degree trinomials. This is an odd power there. And every single one of those terms, these three terms, have a common factor. So with factoring, if you don't ask yourself about the greatest common factor, you could be stuck for the whole rest of the day. Okay? So again, I'm trying to be silly by saying write this on your palm, but I'm not silly if you write GCF as a constant reminder that that's what you should always be asking yourself. Then notice this expression, this cannot be solved. That's one thing students have problems with is they take an expression and then they give me answers for it. X can be anything in the world. There's no boundary on what X can be. It's just an expression. If I told you that that expression equaled a number, then you could then try to find the solutions. All right. So notice you have three different factors here, and notice the degree of the expression is 3. It's a third degree trinomial. It's possible, it doesn't always mean you can have 3 unique prime factors. Sometimes this first step is all you do, and you can't factor any further what's in here. But it's still considered factored because you've taken a subtraction problem and you've written it as a multiplication. Okay? So factor, again, remember, is a verb, it's an action, and it takes an addition and subtraction problem and it rewrites it as multiplication. All right? All right, so you all were working on this, and I see success as I looked at the boards. I looked around to see what kind of summaries I noted, and I noticed one person did this. X plus AI times X minus AI equals X squared plus A squared. So this person just reversed. They looked at the answers, and they went back to the beginning. Did anybody try to write out what they observed in words? Did anybody write anything in there? How do you know it's wrong? What'd you write, Kenneth? Oh, you left the eyes totally out. Okay, yeah. If you had x plus a, x minus a, then that would be x squared minus a squared, which is the difference of perfect squares, which we learned how to factor back in an intermediate algebra class. So this is the first time you're seeing sums of perfect squares factored. And guess what? It doesn't even have to be sums of perfect squares, because notice 7 isn't a perfect square. And the number that goes in front of I is just the square root of 7, just like the number that goes in front of I here is the square root of 25, which is 5. And the number that goes in front of the i's here is the square root of 16. So some people write it like this, x squared plus a squared. And they write this, x plus a, x minus a. One of my students in the last class just did this, x squared plus y. He didn't care to write it as a perfect square. So this is more like what this last one looks like. He wrote this. Just take whatever the square root of that number is, put an I after it, change the sign. Okay. So anytime you're asked to factor now the sums of perfect squares, you can do it. You no longer have to say they're prime, because we've introduced that whole new number system with complex numbers. Okay, and last one did this one on the board, and that is true. The one mistake people make here, or at least the one mistake that seems to be popular today, is people forget the order of operations. The order of operations here says that you have to do exponents first, and then you multiply. So this does not equal negative 40 to the 2/3. That's not correct. You don't multiply until after you figure out what negative 8 to the 2/3 is. And Again, negative 8 to the 2/3 says take the cubed root of 8, of negative 8, and then square it. So this is negative 2 squared, which is 4. And then 5 times 4 is 20. So if you work this out, it will be a true statement. Last one did it correctly. Okay, this idea we're going to be using over and over again today, and it deals with this exponent property. And this exponent property says when you have a power, x to the a is called a power. So the way we verbalize this is we have a power, that power being x to the a, and we're raising x to the a to another power called b. So when you raise a power to a power, you multiply the exponents. You multiply. So this question now becomes, we're trying to figure out what number must that question mark be? So when we raise x to the 3/4 to that number, we get x to the 1. So this becomes this equation. 3/4 times what number gives you 1? 3/4 times what number gives you 1? 4/3. Reciprocals. The product of reciprocals always bring you back to 1. So the question mark is 4/3 because 3/4 times 4/3 is 1. All right, I'm going to leave this challenge off for now because there's a lot to cover today. I do want to point out that if you go to page 49, which I've learned to do because Ken always asks me which page, so if you go to 49, you're going to see what's called an equation summary study aid. Now, Caitlin and I put this on here to try to help you prepare for your first test, which will be on Monday. Friday will be a review of the first 8 classes, and Monday will be a test on the first 8 classes. So Caitlin and I put this together, and so far we've covered linear equations, we've covered quadratic equations, we've covered, well, linear and quadratic come under polynomial, but today we'll be looking at things other than linear and quadratic. We've covered equations involving radical, whoops, hang on, where are we? This is today and this is today. And, whoa, I'm clicking everywhere. All right, so there's one, and then we've covered rational equations. That's the one I was looking for. Okay, so those are the equations that we've worked on already today. And everything else today that we do is really going to use the strategies that we've already learned for linear equations, quadratic equations. Okay, so it's just applying them to a new type of equation. So today's class, this is class number 8. This is class number 8. This is class number 8. Everything that's not circled, you could write class number 8 to refer back to your notes. So what you should do for Monday is you should take each one of these types of equations and in your own words, try to write down the steps that you use. And then over here, put an example so that Monday, if you see an absolute value equation, you can pull out your cheat sheet and look at what you've written and how you solve it and apply it to Monday's absolute value equation that you'll see on the test. Yes, one cheat sheet, one, if you read your syllabus, it's one 8.5 by 11 page cheat sheet, both sides. So what Caitlin and I's suggestion is that you use this as one of your sides, and then the back side, if the back side has writing on it, you can just put a blank piece of paper there and staple it, or make a copy of this and have the other side be blank and fill that out. But this will take care of a large part of your test right here. Okay, so let's get started on these equations, and let's see how we're going to approach them. So the first type of equation is a polynomial equation, And the first thing you're going to see is you're going to see a lot of powers of a variable like x, and you're going to go, uh-oh, what do I do? Well, we're going to use the idea of factoring polynomial equations along with, do you have a question, Spencer? Yes. I was just bringing you to class 49 to show you the study aid, okay? Okay. So the zero product principle, remember, involves the idea that if you multiply, in this case, two things that equal zero, and remember, A and B here aren't just numbers. They could be things like this. They could be represent any quantity. We could have three things if we wanted. We could have A times B times C is zero. And the same idea applies that if we have a multiplication problem that equals zero, then it's possible for each of those factors to be zero. That makes the whole equation true. Right? So one of the ideas, the first thing we want to do is we want to get all our terms here with x in them all on one side. We want to set the equation equal to zero as our first step. So set the equation equal to zero. And you're used to doing this when you solve a quadratic equation. And remember, a quadratic equation is a polynomial. It's a special polynomial. And the thing about the quadratic equation is we actually have a formula to solve it. Once we get beyond quadratic, we don't have one formula. So you could never use the quadratic equation on this. Why? No. It doesn't work. Why doesn't it work? It's a fourth degree equation. A quadratic equation only works for second degree. So the highest number you see all the way across has to be a 2. And we've got a fourth degree. So this is a fourth degree polynomial equation, fourth degree polynomial equation. Okay. So you got to make sure you identify it. You know what you're looking at. Thing you want to do is set the equation equal to 0. So you subtract 6x squared from both sides. Notice I'm saying both sides. So the next thing I write better have two sides, or I don't even look at it for the rest of the problem. Because if you now do this, and you leave it like that, you're not solving any equation. That's just an expression. You can't possibly solve that because it's not set equal to anything. There's any number can go in there. So you solve an equation. Here's an equation by writing an equivalent equation equals 0. All the way down, I want to see that equals 0. Or wherever you stop writing equals 0 will be where I stop giving you points for grading it. Okay, that's how serious I am. Okay. So you've set the equation equal to 0. Now what's a poor algebra student to do? No, not a common multiple. You're close. Common factor, right? So you want to find the greatest common factor, which is x squared in this case. So the first form of factoring is to factor out x squared and write in parentheses what's left equals 0. So now you have a multiplication problem equal to 0. And you could get part of your answer right now. You could say, when does x squared equal 0? Well, when x is 0, there's a possible answer. All right. But the question is, what's going to make that equal 0? And again, it's kind of hard to look at an addition and subtraction problem. So if you can rewrite that in the form you're used to writing as a product of two binomials, then you can factor that, and we can set all the three factors equal to 0. So here we're looking for factors of 6 that differ by 1, factors of 6 that differ by 1 are 3 and 2, and the 3 is going to carry the plus sign, and the 2 will carry the subtraction sign. And now we have three things that equal 0. This is just like this. A times B times C is 0. So you set A equal to 0. A is x like the x squared. You set the B equal to 0, x plus 3. And you set the C equal to 0. And now you have baby equations to solve. This first equation is quadratic, but it's no big deal because it's the simplest one you can get. X squared equals 0. has one answer, x equals 0. X plus 3 is a linear equation, so there your answer is x equals negative 3. And your next one's a linear equation, x equals 2. So you have these three distinct answers. Later on, when we cover polynomial functions, you're going to see that we're going to say that it has 4 answers, but we'll get to that. 3 of them distinct. So again, GCF, and then factor, factor, factor. Set up, keeping everything equal to 0. And then you set each factor equal to 0. And solve for x. Okay. All right. Yep.
Why don't we were doing this, like, without really thinking about it too much, I was thinking of info because it's a fourth degree, there'll be 4 answers.
Yes.
So really, you'll only ever have 2 fourth degree
No,
answers.
it does have 4. And I know you're saying, what do you mean it has? And I was trying to avoid this conversation today because I got involved in my first class with it. It's just that this one's an identical twin. Because it's 0, yeah,
0.
yeah. And if you set this,
Plus or minus value to 0.
because 0 doesn't have an opposite. It's the only number. So you could say plus 0 and minus 0. It's still 0.
Could it have 5 answers? Or would it
Could have potentially 5. It will always have 5 what we call zeros, but they may not all be real. And some of them might be the same. So we say this has 4 zeros, but 3 of them are distinct zeros. And if you were to graph this, if you were to graph this, I'm just going off here on the side for this type of expression, it's unique. In other words, it's x plus 3, x minus 2. If you had x minus 3 and x plus 2, that gives you an entirely different expression that looks like this. Your middle term is negative because when you do your inner term, you get negative 3x and your outer term is positive 2x, which gives you the negative 1x. So often you can come up, you get the right numbers here, the 3 and 2. Sometimes you just play around with this, with the addition and subtraction until you get the proper sign for your middle term. Okay, so one other big thing I want to say about these equations is this. X to the 4th plus, what was it, x cubed minus 6x squared equals 0? Or even before we got there. I know I'm probably barking up the wrong tree. Does anybody remember the commercial for Libby, Libby, Libby's on the table, table, table? No? No, it wasn't that one. How about habitant soup? You mustn't ever put water in a habitant soup. You don't remember that commercial? All right. Well, anyway, you mustn't ever divide an equation by x or a power of x, ever. Because if you did this, notice what you get left. You're going to get x squared plus x equals 6. X squared plus x minus 6 is 0. And look what happens when you factor that. How many answers are you going to get? How many solutions? 2. How many did we have originally? 3. And what you did is you divided, when you divide by x squared, you lose one of your solutions, and you're also dividing by 0. So you can't divide by x squared or x because it's part of your solution. You'll actually lose one of your potential solutions when you do that. You don't know. You just never do. It doesn't even matter that it's 0. You don't divide by an expression because you'll actually drop out one of your potential solutions. One of your factors will be gone, Ramsey. See?
Yeah, I get that. But can't like x squared is 0.
If you have
0, even divide by x squared.
Can you divide by 0?
No, not really.
Work through all your class activities. Your discriminant will tell you whether you can factor it or not. If you put in B, A, and C and it comes out to be a rational number, then you can factor it. If it comes out to be something like the square root of 7, you can't factor it. If it comes out to be something like the square root of a negative number, You're not going to be able to factor it. So if you put in B here, just to answer Nick's question. Okay, next question. This is the thing that we call the discriminant. It's underneath the radical sign. This is 625 minus, someone want to multiply 4 times that for me? Never mind. All right, and you get 49. 49 is a rational number, which tells me I can factor that thing. So it might be worth a couple of minutes just to write all your different factors until you see which ones add up to 25. Now, the minute you start with these extreme factors like 144 and 1 and 72 and 2, the numbers those add up to are huge. And look at the size of your middle term. So that means you should start working in the middle with your numbers like 6, 8, and 9. The other thing, another little trick is 144. If you add the digits of 144, you get 9, which means 9 is divisible by 3, so isn't 144. So the minute you do 3 times 48, you also know several other factors. You know factors of 48 like 6 will divide it, like 8 will divide it, and then 48 also has another 3 as a factor, and 3 times 3 is 9. So there's lots of ways with just a little bit of effort that factoring could become a lot easier for you. Okay. All right, so the moral of the story here is you don't put circles around those answers. Why not? Because every time you have a radical equation and you are squaring or cubing or raising the fourth to the fourth power on both sides, you can introduce what we call an extraneous solution. If you go back and check these in your original equation, which was this, that was your original equation, and I put a 16 in there, that does not equal 12. But 9 works. 9 plus the square root of 9 is 12. So this is extraneous, and this is your only solution. Any questions on this, whether you use quadratic or you factor?
So you got 16 plus.
Yeah. Does it equal 12? No, that's why it's not an answer die. Okay? All right. Yep. Okay, I'm trying to move on, but I can see I can't move on, so let me scroll back down. Yep, go ahead.
Why instead of x square root of x square, just square root?
So you're making up a whole new equation, like x squared. So if you had something like this, x squared plus the square root of x equals?
No, I see. Now we have x plus square root of x.
Yes. Now you want to throw a 9 in to check? Okay, let's do that. All right, so now I'm going to check my 9. X plus the square root of x is supposed to equal 12, so I throw 9 in where I see x. 9 plus 3 equals 12. 12 equals 12. You're a happy camper. Okay, that's your solution. Okay? Okay. Any other questions? All right. Now, that's a radical equation. Guess what? A rational exponent equation can be made into a radical equation if you want it to be a radical. So you could solve this. You could take this equation and write it like this right now if you wanted to. If you want to turn it into a radical equation and solve it like we just did using the techniques we just did, it's fine. You would add 6 to both sides. You'd get 3 times the 4th root of x cubed equals 6. Again, you want to isolate your radicals, so you divide both sides by 3, and you'd get this. And you would now use the techniques we did earlier. I don't want to show you the radical. I want to show you the other approach. When you have an equation with a rational exponent, instead of converting it, this should, oops, there's a typo right here. This should say radical equation. So one method would be to convert it to a radical, and we just went over how to solve radicals. Or you can raise both sides to the appropriate power to get x to the first, which is what we did in our preview exercise. Before you do that, however, you want to get x to your rational exponent. You want to have a 1. You want to solve it just like as if it were a linear equation. So let's do Fantasyland here. Here's Fantasyland. Fantasyland would look like this on a test. I would give you an equation like that to solve, right? And you'd all be very happy. right? So in fantasy land, what would we do first to solve that equation? Plus 6 to both sides. So guess what? We're going to do the same thing here, just like we're in fantasy land. So we get 3x to the 3/4 equals 6. And over here, we would have 3x equals 0. Okay, let's stay in fantasy land. What would we do next? Divide by 3 on both sides of the equation, and we get x, in this case, would be 0. Oh, that's a 6, would be 2. All right. So again, we want to divide both sides by 3, and we get x to the 3/4 equals 2. Okay, so now we're out of fantasy land because we don't have x here. We have x to the 3/4. What we want is x to the first power. All right, we want x to the first power because we're solving for x. So this is where our preview exercises come in. I want to raise this to its reciprocal power, which is 4/3. Yep, I want to take the reciprocal of 3/4, which is 4/3. And whatever I do to one side, I do to the other. So remember, when you multiply 3/4 times 3/4, you get the number 1, and your answer is 2 to the 4/3. And you just leave it just like that, because you can't simplify it any further, because the cubed root of 2 is an irrational number to simplify. So you leave it just like that. So when you have a rational exponent equation, be in fantasy land for a minute. Even on the side of your paper, you can make it look like 3x minus 6 or whatever your equation is. Then do the same exact steps, and then finally just put your x to whatever the power is and go from there. All right? You would get, yeah, you can, go ahead, put it in. Yes, which we can just write like this. So how do I do this? How do I evaluate this right here? It's a power to a power. What do I do to those powers? And what happens when I multiply those powers? I get 1, right? I get 12 over 12, which is 1, right, Nick? So that's 3 times 2 is 6 minus 6 is 0. Happy camp. Okay. So there's no sense in putting it in radical form like cube root of 16, because then that's really hard to figure out what to do from there. Keep it in exponent form, it's easier. All right, there's probably nothing where I see, other than squaring things like x plus 2 square and seeing the wrong answer for that. I don't know what it is about absolute value equations, but students really get confused with solving these. And the best thing I can do is to just say to you, if you take the absolute value of anything and you get 11 for your answer, whatever's inside that stuff, inside here, let's call it stuff, then the stuff inside, this stuff, could either be a negative 11, right? Because the absolute value of negative 11 is 11. Or what else could the stuff inside equal? Positive 11. So I would suggest when you start off with an absolute value equation, give yourself a little help. You always have to have your absolute value on one side of your equation and your constant on the other. Once you get to this step, take whatever's inside there and call it stuff. Say, okay, my stuff can either be positive 11 or its opposite. And draw yourself a little number line, just like that. Now, take stuff and write in what the expression is. So that stuff, 2x plus 1, is going to equal negative 11. Or that stuff, 2x plus 1, could equal a positive 11. And notice you have two baby linear equations to solve. 2x equals negative 12. X could be a negative 6. Go back and check. 2 times negative 6 plus 1, absolute value. Negative 12 plus 1, absolute value negative 11 is 11. Yep, that works. Or 2x plus 1 could be a positive 11, and we're still okay. 2x equals 10, x is 5. Okay, so you have two answers. I don't know if it's wise to show you the mistakes that people do, but I want to show you one of the popular things. Students will often end up getting the right answer because what they do is they just drop the absolute value sign like it was a parenthesis. So they'll just do this. 2x plus 1 is 11. And notice that gives you one of your equations. So you'll get one answer. Many times students who do these will get one answer. And you forget that the stuff inside could also be a negative 11. But the biggest error is when you have something like this. When you have, let me just extend this page. Let's suppose we had the same stuff inside like this. And I'm going to put 12 over here for a minute. And you had a number out here. Okay. You still want to isolate the absolute value like you do any equation where you're trying to solve for x. So the first step you should do here is to divide both sides by 3. Okay, so you get your absolute value one side and your constant on the other. But this is what students do. They treat that absolute value symbol as if it were parentheses, and they do this. They just distribute through. And again, you'll probably be okay for one of your answers, but not the other. So in other words, if you divide both sides here by 3, you'll get 4 over here. And if you drop those absolute values symbols and just do this, you'll get 2x equals 3, x is 3/2. You'll get the same answer over here. You'll still get 3/2 over here. So the moral of the story is when you have these absolute value symbols, if you have anything multiplying it, divide both sides of your equation by that number. If you have something added and subtracted from here, move it over to the other side. And then remember that the thing inside the absolute value could be the opposite of this number or the number itself. You got two potential solutions. Right? That's the biggest thing about absolute value.
You just remember that, like, when you see absolute value, there's
These two answers aren't opposite of each other. Okay, so even though you have two solutions, they're not opposites of each other. Okay, then I'll come back to this die, okay? The last thing I want to cover, so I can give you at least a good 15 minutes to work on this, is inequalities, and I know you've seen this before a zillion times. Solving a linear inequality is you follow exactly the same steps that you follow for an equation with one little twist. Whenever you multiply or divide both sides by a negative number, you have to reverse the sign of the inequality. Now, sometimes you might get an inequality where you'll never have to multiply or divide both sides by a negative number. So you're all set. You don't have to remember anything. But notice I set this first one up so you have to. The only way to solve for x here is to divide both sides by -4, which is the coefficient. And you get x on this side and -2 on this side. And you have to remember to reverse the direction of that. So now it becomes greater than -2. Yes, because I divided by -4. And that's the only thing you have to remember. Like if I had 4x is less than 8 and I divided by 4, I'm golden. That's my answer. And all you have to do is look at your solution on the number line. In this case, Yulia, right? You can take any number less than 2 and plug it in here, and this inequality is still true. Like, let's suppose I put -5 in there. 4 times -5 is -20. That's less than 8. Now look what happens over here. If this says that all your solution set are all numbers greater than -2, let's suppose you forgot to change this symbol, right? And you took some numbers less than -2, like -5 again, and you said -4 times -5 is 20, 20 is not less than 8. So that means you forgot to reverse your symbol. Okay. All right, then the only other thing is sometimes they combine these types of inequalities. They call them compound linear inequalities, kind of like a compound sentence, right? I could say Kenneth is still writing the answer down to the last problem, and Di wants me to go back to the previous problem. That's a compound sentence, right? Same is true here. You go into your middle and you say, I want to solve for x, so that means I have to add 4. But notice instead of just one other side, you have 2 sides. So you just add 4. That gives you x in the middle. Since you're adding, you don't have to worry about the direction of the inequality changing. And so this is what you get, and you're all done. Voila, that's it. Yep, because you already have 1x. If you had 3x there, then you didn't have one more step. You'd have to divide through by 3. Okay, that goes outside, Spencer, please. Don't shake your head, please. We'll have to have a discussion after class. All right, so you have lots of equations to solve for class activities.